So air enters a turbojet engine at 25, so the pressure over here is specified at 25 kilopascal. The temperature is specified at 215 Kelvin, and an inlet velocity at 250 meters per second. The mass flow rate of the air is 18 kilograms per second, so we have m dot. Air is slowed in the diffuser. The pressure ratio across the compressor is 15. So the pressure ratio, 15, so P2 divided by P1 is 15. The turbine inlet temperature is 900, so T3 is 900 Kelvin. And the work developed by the turbine equals the compressor work input. So what is developed by the turbine is just enough to drive the compressor. That's going to be key. A lot of times we forget that. The isentropic efficiency of the compressor is 75%. The isentropic efficiency of the turbine is 80%. And the diffuser and the nozzle processes are isentropic. So S is equal to a constant, S is equal to a constant. There's negligible pressure drop through the combustor, hence P3 is equal to P2. And the operation is steady state. Kinetic energy is negligible except at the inlet and at the exit. So the kinetic energy at 1 is equal to the kinetic energy at 2. They're all kinetic energy at 3, the kinetic energy at 4. That's all negligible, but the kinetic energy at A is not. The kinetic energy at A is not negligible, nor is it negligible at the nozzle exit. So I want to solve for V sub B. And then I want the thrust developed by the engine. Let's call it FTH, thrust. It's a force. Would it be in something like newtons or kilonewtons? The thrust? Yes. Yeah. And the velocity at the nozzle, meters per second, units. So I know the symbol, I know my units, what I'm looking to solve for. Okay, what you have to do is step through this process. What I would do is I would make a table of all your states and then have double for some states if I know I have to do, I have to do a isentropic, and then I'll have to factor in for the efficiency. So my state will start with state, let's say A, and then 1. But 1s is the same as 1. There's no, it's isentropic. Okay. But now when I go from 1 to 2, I'll go 2s because I'll first analyze as if it had been isentropically compressed in the compressor. Then I'll use the isentropic efficiency of 75%, and then I'll actually get state 2. See my logic? And then at state 3, there's no 3s in 3, it's just 3. But there is going to be a 4s because I'll assume isentropic process across the turbine, and then I'll account for that 85 or 80% isentropic efficiency to calculate state 4. All right, and then I'll have from 4 to B, that'll be it. And really what I'm keen on calculating is the pressure, whoops, got to put P for pressure, in kilopascal, and the temperature in Kelvin. True? All right, now let's go ahead and fill in as much of this as possible. Now, I can also do this. I can make more column. I can make a velocity in meters per second. I didn't leave enough room. And then I can have a kinetic energy column, kinetic energy in kilojoules per kilogram. I could have an enthalpy, but I just want to use constant specific heats, okay? I'm not going to jump back and forth into the table, air tables. I could, but let's just, or you could even, if you wanted to use the temperature-dependent specific heats in the air tables, you'd probably make a column for enthalpy. Okay. Well, let's start off. Let's put in some values that we know. We know that it's 25 kPa, 215, and 250 meters per second. And the kinetic energy, I didn't leave room there, did I? The kinetic energy at A is going to be 1/2 VA squared. True? But the units on that will be meters squared per second squared. If I want it in kilojoules per kilogram, I have to remember a unit conversion factor that 1,000 meters squared per second squared is precisely 1 kilojoule per kilogram. And I like to work in units of kinetic energy in kilojoules per kilogram. Watch your units. All right, now let's go to state 1. Do I know the pressure at 1? No. The temperature at 1, the velocity at 1. I just know it's negligible kinetic energy. The rest of this is all down here, and if I wanted to, that this is my velocity at B, that's what I need to solve for. So the rest of these are all kind of boring zeros. All right, but let's jump in and see if there's any pressures or temperatures that we know. Do we know T3? Yeah, so we could put in T3 of 900 Kelvin, right? Let's take a look. How about pressure at B? The pressure at B, 25 kilopascal. Is there any other that I know? I'm sorry? Pressure, but I don't know the pressures. They're the same value, but I don't know the pressures yet. All right? Okay, so what I have to do is I have to analyze the diffuser first. Control volume around that diffuser, conservation of mass, conservation of energy, and the second law. Well, the second law and the conservation of mass are they're true, but they're standard. They don't really tell you anything. M dot in is equal to M dot out. That's mass balance. And we already know that S is equal to a constant. So anytime I have a constant specific heat process, S is equal to a constant, I can use one of numerous equations for the isentropic process. Maybe this equation would be one to use. I don't know. That pressure at 2 divided by the pressure at 1 is equal to the temperature at 2 divided by the temperature at 1 to the K over K minus 1. All right. Normally you see T2 over T1 is equal to the ratio of the P's to the K minus 1 over K. But I just changed a little bit algebra, right? So that's the second law, essentially. Ideal gas, air, isotropic process. I didn't use the first law. I didn't use conservation of energy. Let's use the first law. What does it tell us about this control volume? It says the inlet enthalpy at A plus the inlet kinetic energy at A is equal to the exit enthalpy at 1 plus the exit kinetic energy at 1, which we just said was negligible. So you could, we recall, how about this one, that the kinetic energy at A is equal to C sub P T1 minus TA. I'm running out of room. I introduced constant specific heat times change in temperature is equal to change in enthalpy. Follow that? What can I calculate? I look at this equation. I got the kinetic energy coming in based on the speed coming in. Specific heat, I'll do a cold air analysis, 1.005, somewhere in that vicinity. I'll have the inlet temperature, T sub A, only one unknown, T1. Make sense? Did you follow the logic? All right, so the temperature at 1 comes in at 246.1 Kelvin. Did it go up or down? It went up because it converted the kinetic energy into increased enthalpy, and enthalpy is a function of temperature. Enthalpy went up, temperature went up. Now we use the second law, this equation, to calculate the pressure. The pressure at 1, you can unravel that equation and calculate that it's 40.1 kilopascal. What did the pressure do? It went up. It went up. That's the purpose of the diffuser. Slowed it down, temperature and pressure go up. Okay. Now, what about the pressure at 2S? Pressure ratio. Pressure ratio was 15. So I multiply 15 times 40.1, I get 601.8. Is that going to be the same pressure as the 2S versus state 2? Yeah, what we're going to do is we're going to do a pressure calculation, and then we're going to say, but it wasn't isotropic, so I'm going to have to go back and have more actual work in for the same pressure change for our compressor. Right? So that is 601.8. And guess what? Constant pressure through the combustor? 601.8 kPa. Right? All right. Now I have to find the temperature at 2S as if I had isotropic compression. Here's our favorite equation. You just use it again. This time it'll be T2S divided by T1 is equal to P2 divided by P1 to the K minus 1 over K. That's the one you're more familiar with probably. And that allows you to calculate temperature at 2S. Temperature at 2S is 532.9. Did you follow me on that? All right. How do you calculate temperature to actual? You need the isentropic efficiency of 75% for that compressor. Have you done those calculations? Right? Do you want me to slug through it or give you the result? Just do it. So I'm going to have to probably erase somewhere because I don't want to keep flipping around here. Let me see where I can fit it in. Erase the table? Don't erase the table. All right. Okay. So the efficiency of the compressor is equal to the work that the compressor, as if it is isentropic, over the work compressor actual. Do you like that equation? Okay. That work compressor isentropic is H2S minus H1 divided by H2 actual minus H1. Using constant specific heats, it's C sub P divided by T2S minus T1, C sub P T2 minus T1. The C sub P's cancel. Cold air analysis, constant specific heats. Okay. So in this equation, I know the efficiency. I know T2S. I know T1. There's only one unknown. True? So I leave the algebra. And is that temperature going to come in higher? 628.6 because of the irreversibilities in the compressor. It's the same pressure, but you had to put more work in, hence it comes out hotter at state 2. Now, typically these are given by fixed, how much fuel you burn, often metallurgical considerations, but this one isn't on takeoff. This altitude, this aircraft is cruising. It's cruising up where it's nice and cold and low pressure. It's like 35,000 feet. It's the inlet pressure and temperature right there, okay? And about that cruising speed is for the inlet conditions at A. So it's not gunning it, right? It's not on takeoff. So it's just burning enough fuel and you have 900 Kelvin. All right. Now, what about what's happening across the turbine? You have to develop just enough power to drive the compressor. So you start with the equation that the work that the turbine actually produces is the work that the compressor actually, if you want to put an A there to emphasize it's actual work, not the isentropic. Right? Okay, so let's do this. What is that work, the compressor actual? You could put the C sub P, you have the T, I just wrote it, where is it at? It's T2 minus T1, right? And then for the other side over here, you have C sub P times T, 3 minus T4. True? Did I do that right? I'm kind of using bad math. I have a run-on equation, right? It's like a run-on sentence. It just goes for the whole paragraph. And I have 3 equal signs in one equation. But I'm trying to conserve space. So basically, the temperature at 4 is equal minus the. This is known. Temperature at 3 is known. The temperature at 4 is the only unknown in this equation. True? So I calculate the temperature actual at 4. Okay. I come in at 517.5. This is kind of backwards, isn't it? Right? All right. Now the question is what is the temperature for isentropic? How do I, or what I did actually was I calculated the work or the turbine actual. That's the C sub P times that delta T, T3 minus T4. Got it? Then what I did was I take and use the isentropic efficiency of 80%, so the work, the turbine isentropic, would be 1 over the efficiency, isentropic efficiency of the turbine, work turbine actual, and so I got the work would be a lot more out. It would be a lot more out, okay? Which is C sub P times T3 minus T4S, which means the temperature at 4, if it would have been isentropic expansion, would have been a lot lower. And I calculate then that's 421.9, because that's one equation with one unknown, T4S. Good?
Do we actually need that?
Yes. And this is why. I don't know the pressure. But the only thing that allows me to get that pressure was isentropic down to a certain pressure. I have the compressor pressure ratio. Is that a tongue twister for me? The compressor pressure ratio, but I don't know the turbine pressure ratio. And to drive the nozzle, I want a high pressure to feed the nozzle, to really push it out at high speed to give me good thrust. True? So this helps me now. Now that I know T4S, I can come back to an equation like this to get P4S. Does that make sense? It's like I've used the same equation expressed either with the pressures on the left or the temperature ratios on the left a couple times now. And I calculate then the pressure is 42.3 kilopascal, which is, by assumption, the same as the pressure actual at the inlet to the nozzle. Well, guess what? Now I can, with that pressure and that temperature is the actual inlets to the nozzle, this is the exit pressure to the nozzle, I can calculate the exit temperature, TB. How would I do that? What's constant? S is equal to a constant. It's an ideal gas. I use this equation again. Do you follow? Or did I lose you? You're following me? It's like, man, I just keep going back to use that same equation. I did it for the turbine isentropic process through the turbine, did it through the isentropic process through this nozzle. Okay, so what we find is that the exit temperature at B is 445.4. It's still hot. Hot gases are going out. All right. Now I want to calculate the velocity at B. You tell me. I just got all the pressures and all the temperatures. I used the second law around the nozzle to get the exit temperature. What law do I use to get the exit speed? First law, just like the diffuser. True? You got one. So the equation is you have H4 plus the kinetic energy 4 is equal to HB plus the kinetic energy B. This is negligible, inlet kinetic energy to the diffuser, to the nozzle, such that you have the kinetic energy at B is equal to C sub P T4 minus TB. True? And I calculated, I forget what I calculated on that. But then once I have this kinetic energy, isn't that 1/2 VB squared? Isn't that the kinetic energy at B? And I have to always remember this unit conversion factor right here. Right? Because the C sub P is typically kilojoule per kilogram Kelvin, and you want speed in meters per second. And you calculate the exit speed is 380.9. So V sub B is 381 meters per second. Okay? Yeah, slow, but hey. Now, it asks us to secondly calculate the thrust developed by the engine. I'm going to put it right in here, okay? If it'll allow me to erase, please erase. Thank you. So what is the equation for the thrust force developed by the engine at cruising? It is cruising. I'm not trying to take off, just cruising. 35,000 feet. What is the equation? It's the mass flow rate times the velocity on the exit minus the velocity on the inlet. Good? So we put in our equation, in our 18 kilograms per second, and I'm going to tuck it right up here. The thrust force is calculated to be 480. Whoops, I messed that up. You know what? I don't have it in my notes. I have it somewhere else, but I don't have it in my notes in front of me. So multiply 18 times 381 minus 250, and you'll have it. Well, look at the units. It's going to be kilogram per second times meters per second, kilogram meter per second squared, Newton. All right? All right. We done? Yes, sir.
For our specific heats, especially the C sub P, how do we calculate that? We don't want to use.
Okay, well, if you want, I'll flip to an Excel spreadsheet, and I can show you this all done in Excel. You know I didn't do this by hand.
Right.
I would make too many errors. I'd make too many errors.
If we wanted to calculate it by hand.
Yeah, you do that by hand, and you don't make errors, but you would use a specific heat, and if you did a cold air analysis, 300K. But then the next thing to do is I said, I want to redo the calculation. I took the average of all of these temperatures, and I redid it using that specific heat. And you know what? It is very good compared to the more detailed going into the air tables. It's close enough, believe me, for these calculations. Well, I just took the average of all these temperatures and pretty close. Okay. Do you want to see it on Excel or not? Thumbs up, yes, Excel or no? All right. So do these pressures and temperatures agree with the ones I wrote down? About this velocity of 390.9. Here you can see I played with the kinetic energy in kilojoules per kilogram. Here are the calculations for the change in the enthalpy, the change in the temperature. Then I brought that temperature up. Here is the efficiency, isentropic for the compressor, isentropic for the turbine. And okay, so it looks like it developed about 2.4 kilonewton thrust from these calculations. But then I calculated the average temperature. And so the average temperature, I started with the temperature of 300. And when I evaluated this specific heat, it used that temperature. So all I did was take that chunk of code, flip it down, and now replace by that temperature. So if you kind of look at now this next block of code right here, where I'm using an average temperature of almost 480. It doesn't look like it changed the specific heat that much, does it? And the K is just almost 1.4, but it really does make a difference in the calcs, and so you're now at 2.93 and 413 meters per second. 413 meters per second and 2.93. There's the average temperature. I made one more iteration, and you're done. Okay, you're good. Any comments, questions about that? Did that help looking at the Excel code? What did I calculate right here in this column? Mach number. What is that? Speed of sound. And so the speed of sound at 215 Kelvin isn't not all that high, but I got a Mach number about 0.85. That's about the cruising speed of a lot of commercial aircraft, 0.85 at that altitude, because it's so cold. But you calculate the Mach number of the exit gases coming out the engine, and this Mach number is right at 0.97. So it's coming out because it's hot. It's coming out faster, but it's still subsonic. Okay? So I calculated the Mach number there.